All right, guys, welcome back to Elite SAR training and welcome back to the land navigation portion of our basic search operations course. In this particular video, we're going to start taking a look at the maps used in search and rescue. There are many different types of maps that provide valuable information for both the search operator and search managers. The U.S. Geological Survey topographical maps, like this example here in the top left, this is one of the more useful general purpose maps that we use in search and rescue. Maps like this can be very useful, but they may be a little cluttered. So that's why we want to leverage other maps that are available to us. For example, if we're only interested in maybe the roads or streets, we can look at something here in the bottom left, where we can pull up on our phones fairly easily and provide the most up-to-date street layout information, which can be useful in that urban and suburban environments, or trying to identify points for containment. However, street maps, they don't provide any information regarding the terrain or the vegetation we see in an area, which may be needed if we think the subject is in a wilderness environment. And that's where something like this map here comes into play. And this is an aerial photography map. This is it's aerial photography stitched together from satellites, but it can also be pulled from aircraft as well. And it could be, depending on the source, sometimes this imagery can be collected multiple times throughout the year. Sometimes it's fairly stagnant, and it may take a little bit, there may be a little bit of a gap between when the aerial was collected and published. So it may not be truly representational, and it's a little bit harder to capture and update than street maps, but it's something that it really gives you a good feel for some of those features that may not show up on a road map. Any details regarding roads or structures, in order to give those details, we have to project that over top of the photography, which is the example we have here in the bottom right. So this example here is a little bit of a blend, or more of a hybrid map, where we have both the aerial photography kind of in the background there, but you could see laying over top of that, we have the roads, we have some of those water features highlighted as well. But then you can also see included in the overlay, we see a little bit of texture to the map, and then where we can really kind of get a good feel for the terrain and how it rolls. And so this is another overlay that we could do to really pull out those details. The important thing to take away for maps like this in search and rescue is there's not one type that really is the best overall map for every search. It could be something where you may want to flip through a few different map layers to get the right one for you, or find a way to blend them together to find something useful. But this is the general sense, the basic maps that we tend to turn to in search and rescue. Now there are other maps that are handy as well, and they have their value that they add to the situation. For example, like the top left, where we have the property map, that can tell us something specific about a public location. That may lend us, it'll highlight some of those areas of interest that if someone gets lost in an area such as a park or a large campus, it may highlight some of those areas that we may not be privy to as searchers going into it. Then bottom left, we have an FAA sectional map, which, to give you an idea of the scale, this right here, going back to the map that we were showing previously, it only covered really about right here. It did not cover that much at all. So this is blown way out. And it's much larger because it's intended for aviation use, but it has its value in search and rescue as well. Not just looking for downed aircraft, but if we want to know the locations of like towers or beacons, something with a blinking light on top of it, something that may be a draw depending on our subject profile, turning to an FAA sectional may provide some value to us. And then here in the top, top middle, top right, this is a marine chart. And in marine charts, these are a little less commonly used in search and rescue, but it gives you the depth of the water. So that way, if you're working in and around water, you have reason to suspect that your subject may have entered the water. It gives you an idea of what that topography looks like underneath of the water. And then bottom right, we have a historical map. This is a stitched together, it's actually two maps that are butting up against each other. But these are, what this area may have looked like many, many years ago, which the question you may ask yourself there is, well, why do I need that information? If I have the most current map, I feel like I've got the best map. Understanding some of where those historical roads or historical trails, historical locations are, it may play valuable to us. There may be trails that are, easy routes of travel that have, been grown over the years, but they're still really easy routes to travel. They're just no longer in use. Having a little bit of that context may be useful depending on the search you're on. So a historical map is something that you should also look at as well. So whenever we talk about from the operator perspective, the search operator perspective, whenever we look at maps, there's a few things that we need to look for on the ground level that make the map valuable to us. First of all, the map should be relevant to the search area and the mission that we're on. If the map is the scale of the map is blown way out where there's like a little tiny piece that is only our search area, that's not a map that's very useful for us. And if we're doing some kind of a different search, maybe over water, or a map like this may not necessarily be of value to us on that mission. So it needs to be relevant to the area and the mission. It needs to describe the terrain and those man-made features. So we'll talk a little bit more about how you read the terrain on these maps and how we can identify some of those man-made features, but having that available to you on these maps is a very nice to have at the operator level. And then the big thing at the bottom is it can be used for land-based search and rescue. So the map that we're looking at here, it's a 7.5-inch topographical map or a 1/24,000th scale down here at the bottom. This map scale achieves these requirements. It's something it's blown out where we can cover a fairly large area on this map, but it gives us enough detail to where we can see the terrain, we can see some of the man-made features, and it's something if we need to navigate, we can navigate using this map. And again, maps like this, what you're seeing, have been historically produced by the U.S. Geological Survey, but now can be produced by multiple sources. The ones that I first started on whenever I got into search and rescue were the big, giant, rolled up maps that were in the command post, and you really didn't carry a copy with them in the field unless you made your own copies ahead of time and just had a stack of them with you. Tools and technology has got so much better over the year to where we can now fit maps like this, in our phones, in our pockets. Also, with this particular program here, you can see where this could be easily printed out on an 8.5 by 11 sheet of paper that can be printed on site, relevant to the operations, and handed to searchers as they go into the field. It has come a long way. It's using the good data that the U.S. Geological Survey has collected, but the technology around getting good maps in the field has grown a lot over the years. So taking a look at this map, whenever you first pick up a map, you should really take the time to get comfortable reading it, comfortable understanding the features, what the map is trying to tell you. Taking a look at the map, where are the roads on this map? Where do they come together? Where do the roads come together and intersect? If you were to leave on foot, if you were to walk away from a location, how would you do it? How would you do it using the roads? What would go through your mind if I was getting from a point here to a point, down here somewhere? How would I do that? Those are the kind of things whenever you pick up that map and you're starting to take a look at what is the map trying to tell you. These are the questions that should cross your mind. Where are the water features? You see a river up here, right? You see a river. So how would you get across the river? If you were intending to get to the other side, how would you get across the river? It's the Ohio River, so it's not something I would swim. So I'm looking for a bridge. Those are the kind of things when we're looking at this map that we're looking for. And I challenge you, what else do we see on this map? What else is of interest on this map? So in terms of looking at the map, again, looking at the 7.5-inch topographical map, these are the USGS maps here, and the colors mean something to us. Whenever we see black, that's a man-made object. And I know it may be a little bit tougher on your screen to see, but we have, some black dots up here in the Cannleton area. Those are structures. Those are man-made objects. Some of them are filled in all the way. There are some that just have a black line, and they are the inside of it's white. That means something to us from a map perspective, but it's still a man-made object. Yeah, we also have like these smaller roads right here. These are black as well. They're a different color than the red. The red are primary roads. These are highways or major roads that go through the area. Blue makes sense. Blue is water. Green, it makes sense. It's vegetation. And bear in mind that it's vegetation as it was whenever this map was created. And the same thing with water. That's where the water was whenever this map was created. It may not reflect where we are today, or what it looks like, but it gives you an idea. It kind of gives you a flavor for what it looks like out there. You see a lot of little brown squiggly lines all over the map. Those are elevation contours. They tell us how the terrain is shaped, and we'll go over to how to read those a little bit later. But those brown lines are telling us stuff. They're telling us how the terrain is shaped, where the steep parts are, where the more level parts are. We can start to draw some conclusions based on that. We have this big blob of purple over here in the left side of the map. That's a revision. That's whenever they produced this map, apparently in an earlier version, this is a new addition to the map that was not included in the previous version. So that's, again, the map is telling us, hey, if you've been using this map historically, you see this, there's a change here. All right. So those colors on the map, they mean something to us. And how the contour lines are shaped, they tell us something as well. Like earlier, whenever here in a little bit, we're going to talk about orientating a map to your location. And to really do that, you need to understand what the map is telling you here. So what a river looks like. You can see here, that's where a river is. How is flat terrain represented on the map? Well, it's here. We see an area where there's an absence of the brown contour lines. That indicates that that's flat terrain. We start to see a lot of contour lines put together somewhere. That indicates that it's rough terrain. We see an area where there are a lot of circles that seem to mound on top of each other. That represents that's a hill or some kind of a specific point that rises above the terrain around us. So that tells us that it's a peak, or it's a hill of some sort. It's some kind of something rising above the rest of the terrain around it. We have a hill here and a hill here. This area in between is called a saddle. That area in between is called a saddle. So why is that significant to us? That's potentially an easy route of travel. If someone is looking to get from here to somewhere on the map over here and they don't want to walk all the way around, or they can't walk all the way around, this saddle may be an attractive option for them to navigate through. Okay, again, the shapes, it all means something to us here. A creek, you see the blue line here on the left side of the map. It kind of snakes its way through here. That's a creek. It's blue, it's water, but it's much smaller, as you can see, than the river over there to the right. So that indicates that it has water in it, and because it's not hashed, you see over here there's a blue line that's like hashed a little bit. That indicates that it's an intermittent creek. It has water in it sometimes, not all the time. You see a solid blue little line like that, that means that there's water in it all the time, or there should be water in it all the time. Okay, creek. A lake, you see a giant blue blob on the map, that's going to be a lake for us. You'll sometimes see the smaller ones, or you'll see it may be a blob with what looks like little lily pads in it. It may be a water source doesn't always have standing water in it. Maybe kind of just a swampy or marshy area. But you see a larger blob like this, it's filled in completely. That's going to be a lake or a pond. You look here, you see a valley. You see over here to the south some rough terrain down this way, and then you have some more rough terrain kind of up here to the north. This area in between, it's a valley. Okay, we see rough terrain on both sides, so this is going to be down below. You see a water source running right down the middle of it. That's a valley. A ridge is represented here. You see how we have this point where we have some rough terrain going up and it kind of looks like a finger. This is a ridge. This middle part right here is called a ridge. Okay, and to contrast that, this area in between these two ridges, because we have a ridge here and we have a ridge here, this area in between, this is called a draw. Okay, it's called a draw. So we have a ridge right here. This is where we are going from lower level to higher level. We have a ridge here and a ridge is here, and then this area in between is a draw. An easy way to remember to distinguish those two is whenever you make a fist. If you make a fist with your fingers, the bones on your fingers are going to be the ridges, and the spaces in between your fingers are going to be the draws. And that's what we see here on the map as well. Okay, so this is just to give you a little bit of an idea, looking at the map, what the terrain is, what it's trying to tell us. And this is not an all-encompassing list. There are other things that are not included on this that would be interest of us, but this is the high level, probably the most common things that you'll run into looking at a map. All right. We'll continue on around the map here and just talk about some of the things that you see around the map here. And the first thing I want to point out are we have all of these numbers around the edge of our map here. This means something to us, and these are our UTM or our USNG. These are our U.S. National Grid. These are our primaries. These are used for land navigation. We'll go into depth on this a little bit later on, but what these are used for is to break these larger zones into little small 1 square kilometer grids or squares. This is useful whenever we're navigating using a paper map. Down here at the bottom, you'll see the projection down here at the bottom. It says Mercator projection. The map projection is largely irrelevant for the purposes of this training, but for those of you using a map on a much larger scale, this becomes much more important to understand the projection. And I don't want to get down in the weeds too much on projections, but you are certainly welcome to Google Mercator projector on your own if you're interested in learning more. But this tells you a little bit, what this tells you is how the spherical object that is the Earth, how it's being represented on a flat 2D surface is what that's telling you there. Map datum is another thing of interest for us because this talks to specific coordinates. It's a very technical component of the map, and it's used to. But the map datum is the survey that was used to define the projected coordinates. Looking at this particular survey was completed in 1984. That's what the 84 represents. And this one in particular, the WGS 84, is the current standard for GPS units. This is whenever you buy a brand new GPS unit, this is the default datum. And the same thing with your cell phone, it uses that datum by default. This is important because for navigation, because the same coordinates can be represented at two different locations depending on the map datums used. To simplify that, so say if I took if I was standing on the middle of the bridge here, if I was standing on the middle of this bridge, depending on what map datum I'm using, it may be two different coordinates depending on which survey you use. The older surveys are going to have, it's going to be represented in a different way. And how you tell it apart and how you get everybody on the same page is that's where you have everyone align on your map datum. Me personally, everything new out of the box uses WGS 84, and that's you don't have to make any changes to any of your equipment. So I usually leave it like that and build. If I'm building a map, I build it around that particular datum. The older USGS topographical maps, they use the NAD 27 datum because again, this survey was completed in 1984. So a map that was generated in the 1950s is using an older survey. But if you look at the map, it'll tell you towards the bottom what datum they're using, okay? So those older maps are going to utilize a different datum, typically the NAD 27. And these are still widely used in search and rescue. I can tell you that on teams that I've been on, looking at the topographic maps that we kept in the vehicles, they use a different datum than what is considered standard today, and that's important for us. So that way, whenever we talk coordinates, we're all talking in the same language. Depending on how far away you are from the center of that survey, the difference can either increase or decrease. If you're closer to the center, it's gonna be pretty close to similar. If you're further away from the center of that survey, then it can be drastic. I know that I've been on one of the more recent searches I was on was we had an individual say on Facebook that he was lost, and he gave us his exact coordinates. And of course, whenever we got to the exact coordinates, there was nobody there to be found. There was no lost person there waiting for us. So as we were kind of looking around, I thought, well, maybe he was using a different map datum. So I changed the map datum in my equipment, and it took me around like to the other side of a bush. It didn't take me very far at all. So, but it was insignificant there. But the further you get away from that center, the more drastic it can be. But the important thing again is to make sure your teams have a standard map datum and you configure everything to work off the same datum. That is important to us. What we have next on the map here is our UTM, or our U.S. National Grid zone. And we'll go over this with a little bit more detail later, but this tells you which zone you're currently depicting. Where in the world are you according to the zone, okay? Down here at the bottom, we have the map scale. Basically, this is the zoom level of the map. The smaller the number, the tighter the zoom, the larger the number, the wider. Also included in this particular map is a measurement equivalency. So you can take a simple measurement, in this case 1 inch, and you know how far that's represented on your map. This is an important thing to note as well if you're doing any kind of planning or you're navigating by map, knowing the scale, understanding how far distances are according to your zoom level or your scale on your map. Another way to utilize that is with these scale bars, which is what we have above. With the scale bars, these are also used to determine the distance between points on a map. As you see, it works in both kilometers. Oh man, my pen went away. There it is. It works in both kilometers and miles. Both are represented here. And this is something, as we dive further into the land navigation topic, we'll teach you guys how to use those and how you can use those to determine distances on maps. Here we have represented the north indicator. Under the Mercator projection, which is what we talked about here, under the Mercator projection, north is always going to be at the top of the map. Always. Under the Mercator projection. However, there are different types of north that a searcher may need to know about and understand the differences for. So the first one we'll talk about is true north. And then whenever we say true north, that is, if you follow true north, that will take you to the North Pole, meaning the North Pole on a globe. Okay, so if there's like a point that never moves at the top of the map, the top of the globe, the North Pole, that's, if you follow the true north, that's where it will take you. Grid north, which is where you see the little GN right here. Grid north is a little bit different. It's the north represented by the grid associated with the map projection. And I know that's a mouthful and it's a little bit of I'll try my best to try to walk through that a little bit better. The difference between true north and grid north is due to the inherent effect of transforming the Earth's spherical surface into a plane surface. We're taking a round object and we're trying to flatten it out level on a piece of paper here. So, and again, remember, under the Mercator projection, everything is north. Okay, and the top of the map, everything is always going to be north. The difference is going to depend on the map location, the projection used. But so this is telling you, if you were to lay this map down and compare it to a much larger map of the world, in what way is it skewed in order to align with true north? That's what grid north is trying to tell you there. It's trying to tell you what the variance is between the piece of paper that you're looking at and the actual true north. Magnetic north, which you see represented here on as MN on our map, magnetic north is the north that your compass points to. That's the magnetic North Pole, not to be confused with the geographic North Pole. This is the magnetic North Pole. Understand that where you are, you can have a wide variance between where true north is located versus where the North Pole is, the geographic North Pole. And as you can imagine, that's going to be problematic whenever we're trying to leverage a paper map along with a compass to navigate. They don't really talk to each other in the sense of they're aligned in terms of north. The north is different. It's inherently different, and it's always with the way the North Pole works and how it shifts, it's always going to be different, and it's always going to change. So to overcome this difference, we have to make a mathematical calculation called declination, okay, which is represented here on our map. That's what this negative 4.3 degrees means. That's telling you what the mathematical difference is between the magnetic north and the true north. For the purposes of this presentation, this would be more so something I would want to, as we're navigating in a field, trying to cover long distances where the impact of declination or not including declination can have a significant impact on where you land on the other end of your trek. For the purposes of this, we're not going to dive too much deeper into it, but just understand that whenever we talk about north on the piece of paper here versus the north on your compass, there is a difference. And depending on how far you are away from a zero declination, depending on how far you're away from where that line is, the greater this number is going to become. Okay, negative 4.3 degrees. You can get pretty far off. You start to get out to 1,000. You start to get out to 1,000 meters or a kilometer. You can be off by 430 meters. I mean, you can be off, or about 43 meters. You can be off pretty far over the course. So the further you are away, the more that you can be off. So bear that in mind whenever you're trying to go from paper to compass. There's going to be a significant impact in the north there, the declination. Okay, so very complicated. This is a very complicated slide, very technical slide, but these are fundamental concepts that we need to learn if we're going to do any kind of navigating by map. Let's jump back over to contour lines. We talked about contour lines earlier, and you can see them. You can see the map in the background of the slide here. But again, what we're trying to do is we're trying to take a 3D environment and represent it on a flat 2D surface. Is what we're trying to do. You'll see some bold brown lines, and you'll see some lighter brown lines on your map. The bold brown lines are what we call the primaries. They'll have some numbers written on them. As you can see, like right here, it says the number 400 along that brown line. If you were to follow this brown line all the way along the map, it'll have the same number all the way around. It'll always say 400, and that's 400 feet above sea level. We call those primaries, and their usefulness is if we're trying to find trying to navigate, trying to understand what's uphill, what's downhill. We find the next primary to determine which way it's going. So we have a 400 right here. Over here, we have a 450. That means we're going uphill by following these contour lines. We're going uphill, okay? So, and we can also determine from here the spacing between these is 50 feet, okay? There's a 50-foot difference between this one and this one. And so then we can take a look at the lighter brown lines, which are called our secondaries. We could take a look at those and determine how far, we can determine intervals underneath of that on the elevation. We can understand the intervals between those primaries by looking at those two numbers. All right, and you can see on our mountain island here, just a representation of that. So if we take this 3D representation here, project it down on a map, this is what it would look like. Okay, so on the map, this is what we see, and this is what we see more so in real life. Okay, that's what we're trying to do here with the contours. The closer, the further apart the contour lines are, the more gentle the slope is. The more level the slope is. If you see some that are like very much spaced out, so if we added another contour here, this would represent that there's not a lot of change in the terrain between these two points here. Not a lot of change there. The closer they are together, the more steep they are. So if we start to see them to really bunch up on a map, we'll get them even closer here. Get them that we know that that's going to be some very steep terrain. If we see multiple that go and run into the same spot, that means that this is sheer. This is going to be a cliff. Okay. Being able to identify something like that on a map is very crucial. Obviously, we don't want to get anybody hurt or anything like that. So understanding where those hazards are in the environment, we can pull some of that information if we know how to read the map properly. So understanding what the contours mean, understanding the shape, the closer they are together, the more steep it's going to be. It's going to drive a lot of our decision making on where and how we're going to search. All right. So this is a fairly popular item that I've run out there on several courses that we've taught in the past, and that's just to do a little quiz here and try to match up the contour lines in the first column here with what it may look like in the 3D world on the right hand side. So I'll give you guys kind of a moment here. You're welcome to pause the video and start to work through this, but we'll work through these and we'll try to match these up so that way. You guys kind of get a feel for how some of these may be represented on the map. We'll take number 1 here, for example. So whenever I look at number 1, the big thing that jumps out to me on number 1 is this area right here. Obviously, on the right-hand side, it's going to be fairly steep. It almost looks like a hill. If we went back a few slides and we saw the hill there, that's what it looks like. And over here to the left, we have a gentle slope right here, but then we have another hill right here, but it's much smaller. There are additional lines on the right-hand side than there are on the left, so it's a much smaller hill, but it's a hill. So if I'm trying to match this up over here in my second column, this one right here looks like a pretty good match. That one to me looks like a really good match. For number 2, we have a little bit, it's fairly steep all the way around, but we have a little bit elongated over here on the edges. It's a little bit elongated over here, but in here in the middle, it's really starting to peak up. It's really starting to pitch. To me, this one looks like E here. So for number 3, we have two fairly level hills, and we have a saddle in between. Again, let me kind of clear that off there and redraw. So we have, a hill here, and we have a hill here, and we have a saddle in between. The saddle, again, is the space between two hills or two peaks. And it looks like these are fairly flat on top. It looks like they're fairly elongated because it could, looking at our options here, A could be a good candidate and D could be a good candidate. But seeing how that these are fairly elongated, I would say that this is a good match for D here. Okay? For number 4, we almost have the opposite of number 1 here. We have this very gradual terrain over here to the right, and then we have what looks like a peak over here to the left. Okay, so this will match up with C. Okay, and then for 5, we have fairly flat terrain over here to the left, and then we're going to raise elevation over to the right, but it looks like it gets fairly flat on top because this is elongated over here. This looks like a good match for F. And then lastly, we have number 6. Again, we have some very tall peaks, and they're more poignant. They're not as flat as what we have up here. They're not as flat as those. And we still have this saddle between. This looks like A. Okay? So if we're going to clear that off, and we're going to map this out again, This one's going to go here. That one's going to go there. Okay. So I hope you guys did well on this. Uh-oh, you know what? I messed that up, didn't I? Ho, ho, ho. Let's try that again. That's going to go there. That's going to go there, and that's going to go there. That's what it's going to look like. Okay? Just a little fun game to kind of get your mind thinking on contours and how we're going to look at the map there. Last slide in this particular video is we're going to talk about map symbology. You know, looking back at those maps, there were a lot of symbols on those maps, and all of those symbols are going to have meanings for us. The U.S. Geographic Survey identifies over 100 map symbols. There's a ton of them that can appear on our map, and it's in understanding what those are telling us. Again, they identify specific landmarks. They identify easy routes of travel. They can be useful for us if we're trying to identify an area where someone may have gone, or how we can get teams in and out of the search area effectively. We need to understand those. Luckily, there's a guide out there online that the U.S. Geographical Survey has produced that really walks through. It's an easy thing to get printed out and save and refer to whenever you're looking at maps. In 2018, the U.S. Geological Survey, they discontinued the field verification for roads, trails, and structures located on private property, which is it's kind of disappointing, because those, from our perspective in search and rescue, though, having those marked on a map are helpful. It's very helpful for us to identify a structure, to find something on a map that may be a potential draw for somebody. But understanding that there's plenty of risks involved with going on private property or surveying people about their property, but they discontinued that field verification work in 2018. So the trade-off is you may not have those newer details like structures, mine shafts, wells, or other hazards. You will have some updated road information. This by going to this, it makes it easier for them to update those maps from a road perspective a lot more quickly. And you can still look at those older maps. They still do exist, and they're still out there available on the USGS website, to where you can look at those and still kind of pull that information together on someone where those structures or those other man-made locations could be. If you're utilizing an older map, you want to make sure that you can verify the existence of some of those features. The maps that we use on the last team I was on were dated in the 1950s. I would imagine now in 2023, that's probably changed quite a bit, and so some of that may not be there anymore. It may not be well represented. Still could be there though, but that's where you put a map in front of a local. They will be able to tell you what's there, what's not, what's missing from the map that should be there. But you can leverage some locals there to help update that map for you. And what I'll do with this is I'm going to put a link to the description in the video to where you can find this printable topographical map guide. And what I'll do is I'll give you guys some homework. I'll put a link to the map we were looking at, the Hawesville map. We'll put a link to that in the description as well. You can print that out on your own. I'll give you guys a list of features to look for. Print it out, get you a red pen, mark it up. Just take some time to get familiar with the maps, get familiar with the symbology, try to find unique things on those maps, just to get a better overall comfort for it. And that is going to bring us to the end of this particular component of the land navigation module. So in the next video, we're going to start talking about how you can orient a map to your location. So stay tuned. Thanks for watching.